Hello, and welcome to Edexcel demola. And today's lesson we are covering equilibrium, a really interesting topic where we learn all about Mr. Le Chatelier. Let's get straight into it.
Okay, so first of all, we need to talk about dynamic equilibrium. And for dynamic equilibrium, first of all, we need to have a reversible chemical reaction. So the example that we're going to go through with most of this video is going to be this A plus B goes to C plus D, but reversible. So you see the symbol here. This just means that the reaction is reversible. Good to know. Now, for a dynamic equilibrium to be established, we need three conditions. A closed system, we need the rate of the forward and backward reactions to be equal, and we need the concentrations and reactants or the products at equilibrium to remain constant. These are three conditions that you need to remember for a dynamic equilibrium to withstand. Now, just a caveat, when we say that the concentrations are constant, it doesn't mean that they're equal. So concentrations of A and B might not be the same as concentrations of C and D, just that they remain constant at equilibrium, right? And that can even go for both reactants, can be different. Now, here are some graphs to kind of show you. So this dotted line tells me that we're in equilibrium. So we'll just highlight it. Why that dotted line is, they are meant to be straight, but they're telling me equilibrium. And you can see here, concentration, say that this first one is A and this one is B. You can see at equilibrium, the concentration stays the same. And the rate of reaction also is staying the same. If this one up here is forward reaction and that one is backward reaction, that's staying the same. And what we're going to talk about in the next slide is Le Chatelier's principle, which is that in a dynamic equilibrium, the position of the equilibrium shifts to oppose or counteract any changes to the system. And we're mainly going to focus on these four kind of domains. We're going to talk about concentration, pressure, temperature, and addition of a catalyst. So we're going to talk about these factors that affect the position of an equilibrium, starting with the concentration. Now, let's say, for example, concentration of A increases. This kind of notation, like the square bracket, means concentration. Say it increases. Now, like we said, according to Le Chatelier's principle, we're going to work to counteract any change to the system. So the concentration of A increases, we now want it to decrease. So that goes back to normal. Yeah? So if we shift our equilibrium right towards the product, we're going to use up more of reactant A so that it comes down, returning to its initial concentration. So increasing the concentration of a reactant shifts the equilibrium right. If we increase the concentration of a product, equilibrium will shift left and vice versa. So just remember that, very important. Pressure. Now, again, we kind of changed the equation a bit. So now there's 2 moles of C, right? Now, if we've increased the pressure, remember what pressure is. It's kind of the force on a specific area, yeah? Cool. 2 moles of gas on the left, 3 moles of gas on the right. What does that mean? Well, it means that if we favor the backwards reaction, forming more of the 2 moles, the pressure is going to be a bit lower. Whereas if we form more of the 3 moles, more particles are in that same unit of area, meaning that the pressure is going to be higher. So if we increase the pressure of the system, we want to favor the backwards reaction where there's less moles of gas, because that will help to reduce the pressure, because there's going to be less particles per unit of volume. Cool. So that's to do with pressure, and you can kind of see it here, as in like the red does less particles. So if we start kind of forming your backward reaction more, getting rid of some of these blue particles, you can imagine the pressure is going to go down because there's less particles per unit of area. Okay. Temperature as well. This one we need to now think exothermic, endothermic, as we covered before. So exothermic reactions have a negative enthalpy change, and positive enthalpy change is endothermic reaction. So I've said this reaction is endothermic, and I've said that we are reducing the temperature. Now, think about this. Endothermic reactions take in heat, so they're going to reduce the temperature of your system. Whereas exothermic reactions give out heat, so they're going to increase the temperature of your system. So if the temperature's gone down and the forward reaction is endothermic, we need to shift to the left to favor the exothermic reaction, so you can release more energy, more heat, and bring it back up. So that is kind of the rationale behind equilibrium shifts there. And again, we just need to apply this. Say the forward reaction is still endothermic, but we've now increased the temperature. We're going to want to favor it so that it takes in more energy. Now, catalyst is the final one we wanted to talk about. With a catalyst, they don't actually change the position of the equilibrium, funnily enough. They speed up the forward and backward reactions at the same rate. So if the forward reaction increases at the same rate as the backward reaction, then that just means that the equilibrium is just going to stay in the same position. So we don't really need to worry about it with catalysts, but it will help our rate go up. Now, something that's really important in this A-level chemistry is like your kind of considerations, right? So you just need to think about how temperatures and pressures can affect your kind of environment, cost, safety, and we might need to compromise on the yield because of these things. If temperature is too high, a lot of energy demands. Pressure too high, safety concerns. If temperature is too low, then that means that our rate's going to be slower, but that might end up favoring the product that we want to make. So just be aware of those kind of considerations. Okay, and we've got to talk about the equilibrium constant, Kc. What the equilibrium constant tells us, and I think it's kind of poorly understood, but it just tells us where the position of the equilibrium is at a specific temperature. And I cannot emphasize enough, at a specific temperature. Very, very important that you know it's a specific temperature. Now, if our Kc is greater than 1, it means the equilibrium is shifted on the right towards the products. If it's less than 1, it's to the left towards the reactants. If it is 1, equilibrium's bang in the center. Cool. And just know again, very, very, very important, the only thing that is going to shift our equilibrium is temperature. And this will still apply when we do like Kp in second year. Yeah? Only temperature is going to change the Kc value. If our reaction is exothermic, we increase the temperature. Think about it. We're going to want to shift to the left to favor the endothermic reaction, which is going to bring heat back in. So Kc value is going to go lower because it shifts to the left. Think about that. Use different scenarios. See if it works. Now, you need to be able to draw your Kc expressions, very, very important. Remembering that concentration with a kind of compound in the middle is a concentration of that specific compound. Now, say, I don't really like it drawn this way because I think it's more confusing. You can see here, ideally, you're putting your reactants above the products. So products above reactants, my bad. So the products are going to be a numerator, the reactants are going to be a denominator. And then with the powers, your powers are based on the stoichiometry. Yeah? Big word, stoichiometry. So stoichiometry is like kind of the moles, I guess, kind of the molar ratio between each of the reactants on the products, or just the kind of compounds involved in the reaction. Okay. Just know as well, must be homogeneous. So whenever we're doing Kc, must be homogeneous. They can either be aqueous or gas, but they have to all be the same state. So A, B, C, and D in this case are all going to be in the same state. Now, one that I think it is easier when you do an example. So I put up the Haber process, which you should have learned in GCSE. Now, I've given random concentrations, but you can see here, draw out the Kc expression. So Kc expression, we remember, we're going to put our reactants in the denominator, and your products are going to be the numerator. Yeah? So we've done that. And then we need to think about the stoichiometry for the powers. We've got a 2 here and a 3 here, which is why we're going to square the ammonia, and we're going to cube the hydrogen. Now, just sub in these values that you had for your different concentrations. We're just going to sub them in. And when we sub them in, we get a Kc value of 4.267. Simple as that. Stick to that. It's fine. Units you don't need to worry about at this stage. So because the Kc value is greater than 1, our reaction favors the products. Hope that makes sense in terms of explaining Kc. And now it's question time. So we're not really holding back. First of all, I want you to have features of a dynamic equilibrium, and then about conditions for temperature and pressure producing a larger yield of ammonia. Again, we've had that same Haber process reaction. Now, in terms of this Haber process and manufacturing ammonia, this is a bit of a longer question. I'll be honest, we haven't really covered it, and I'll do a detailed explanation about the answer later. So if you can, have a go. If not, pause, wait for the answers. We'll get all into it. Okay, so we're kind of whiz through this part. So we were kind of talking about what conditions do we need for a dynamic equilibrium, and we've said these, yeah? Rate of forward and backwards reaction have to be equal. Concentrations of the reactants and products should not change, they should be constant, and we need a closed system. Just remember the 3, yeah? I don't think these are too difficult to learn. Then in terms of the Haber process, you would have seen the forward reaction had a negative enthalpy change, meaning that it's exothermic. Cool. So low temperature is going to increase it because we want to shift equilibrium right so that we release heat in an exothermic reaction. Now pressure, again, we were looking at the moles. So 4 gaseous moles form 2, yeah? High pressure, high pressure. If there's less moles of gas on the product side, then that means that we want to use a high pressure to go and form it. Yeah, so it's just kind of talking about equilibrium shifts. They just want you to like shifts to the right. I kind of cut off the last bit of the question because we need to go to this bad boy now. Whenever you have this, they mention in the question about moles at equilibrium. Sorry about this. Yeah, they mention about moles at equilibrium, right? So this is at the start. The reaction isn't at equilibrium at the start. They said the equilibrium mixture now contains that. So if we have the moles of ammonia at equilibrium, we need to now go back. We need to go back and figure out what the moles of hydrogen and nitrogen are at equilibrium. So how do we do that? I always like this table. I think it's a good method. So literally, what I'd start with is here. You'd say at the start, they told us 1.2, 3.6, and we assume 0 because it's a product. It wouldn't have formed. And then I look at equilibrium, that was 0.16. So the change is positive 0.16. Now, use the stoichiometry. 2, 3, and then a 1. Yeah? So if this 0.16 is 2, to get 1, I need to do the 0.16 divided by 2. So we're going to take 0.08 from the moles of nitrogen, get 1.12. And if this is a 3, I need to now do like the 0.08. I need to do 0.08 times 3, which is gets me the minus 0.24. Or will just get me 0.24. We're going to make it minus. Yeah? That will give us all the moles at the end. Then we use a formula, moles divided by volume is going to give us the concentration. Get the concentrations of each one. Then we do Kc like normal. Literally, just do it like normal. Have those, and then you're thinking, yeah, that's our Kc calculated. That should be the answer on the mark scheme. Cool. Then I also talked about like your concerns about increasing equilibrium yield and like all that stuff. So exothermic is the forward reaction. So if we lower the temperature, we'll favor it. And then there was less moles of gas. I don't know why I've said 3. It's 2, isn't it? Yeah, it's 2. Okay. But you get the drift. There's more moles of gas on the left. So if we increase the pressure, it favors the right. And then low temperature gives us a low reaction rate. These are the kind of considerations we need. Low temperature, low reaction. High pressure, unsafe. Yeah? So just think about those kind of things. Now, on the mark scheme, I had something about a catalyst, which I thought like, it's quite extra. If you want to add it on, sure, go for it. I don't think there's anything bad about saying it. But I think even if you leave at a catalyst, you can still score like a level 3 response, 5-6 marks. So don't worry too much about that part. And finalement, we are going to look at the A-star tips. So again, I don't really like putting too much of this part of the video, but knowing the conditions for dynamic equilibrium, the big 3, closed system, rate of forward and backward reactions are equal, and the concentrations remain constant. Very good to know. Very easy marks if you can remember it. Le Chatelier's principle, I don't know what's happening there, but Le Chatelier's principle, again, I don't think you necessarily would get asked to like define it or write it out, but knowing how to apply it is definitely really, really important. And knowing about how like concentration, pressure, temperature affect the position of the equilibrium and talking about shifts in equilibrium is really, really important to understanding this topic. The formula for Kc, again, I think if you know how to get that formula, calculations comes easy. So just make sure you can do the formula. Now, units for Kc, they've told you not to worry about for now. There will come a time when you do need to worry about the units in these sort of questions, but we'll leave that for A2 or year 13. And then assuming the Kc value can change with concentration pressure, just know it's only temperature that's going to change this. So just stick to that. Now, hope that video has been really, really helpful in terms of explaining equilibrium. If it has, please like the video, subscribe to the channel, and it would be really, really greatly appreciated. Any questions at all, drop them in the comments below, or any like suggestion about a video you'd like to see, please drop them in the comments below. I'll do my best to answer and make those stuff happen. We've got our TikTok and our Instagram, both at A*demola. Drop those in a follow if you can. But that is kind of all for me for this lesson. So thank you so much for listening, and we'll catch you in the next one. Bye for now.